For decades, software followed a single predictable path. Today, it branches into two distinct approaches: rigid logic and shifting probabilities. The first path is traditional development. It relies on deterministic logic, where human developers author explicit step-by-step rules for the computer to follow. The second path is AI native development. Here, developers orchestrate probabilistic behavior, utilizing models that learn patterns from massive datasets rather than following hard-coded instructions. Choosing between these two approaches has become the central challenge for modern software architects. Applying rigid, traditional code to highly ambiguous, unstructured problems results in fragile applications that break when they encounter the unexpected. Conversely, relying on AI for strict rule-based systems introduces risks like hallucinations and unpredictable behavior in environments that require total consistency. We can evaluate these two paths across four specific dimensions: core philosophy, testing and validation, development speed, and the cost model. The decision made at this fork in the road determines whether a product can scale reliably or becomes an expensive operational burden. Starting with core philosophy, traditional software is built on hard-coded logic. Because the rules are explicit, the outcome is 100% predictable. However, this approach struggles with edge cases or unstructured data that falls outside of the original instructions. AI native development takes the opposite approach. Developers feed historical data and context prompts into a model to manage complexity. This creates a system capable of reasoning through deep ambiguity and adapting to new information. But this flexibility comes at the cost of absolute control, as the system's behavior is based on probability rather than specific commands. These philosophies lead to very different maintenance cycles. Traditional software follows a bottom-up process. Designing the architecture before coding leads to a slower initial build, but results in high stability once deployed. AI development is top-down. By defining outcomes and adjusting prompts, teams can generate a functional prototype incredibly fast. In a traditional system, changing a business rule requires a manual rewrite of the underlying code modules. Debugging an AI issue is more complex. Instead of fixing a specific line of code, you often have to track down subtle data quality issues or refine system prompts over several days. Traditional development trades initial speed for long-term stability, while AI-native development trades predictable maintenance for high-impact adaptability. Next, we look at testing and validation. Traditional systems rely on binary unit tests that provide clear, immediate pass or fail metrics. AI systems require statistical evaluation, using metrics like precision, recall, and confusion matrices. A confusion matrix is a table used to describe the performance of a classification model by showing true and false positives and negatives. Because AI models are statistical, they are susceptible to model drift, a gradual degradation in performance as real-world data changes over time. Security also scales differently. Traditional software relies on encryption and secure coding to protect data and authenticate users. AI introduces new vulnerabilities, like adversarial inputs designed to trick the model, or attackers attempting to corrupt the training data. Finally, we must consider the cost model. Traditional software runs on standard servers, which generally results in fixed, predictable operational costs. AI software relies on expensive GPU compute power or third-party large language model APIs. This creates a variable cost structure, where per-token pricing means operational expenses scale unpredictably based on how users interact with the system. Adopting an AI-native path shifts the primary engineering burden from upfront coding to continuous monitoring and managing volatile usage costs. Success starts with learning these concepts deeply before attempting to build them. We can use a simple decision tree to determine which path a specific feature requires, starting with the primary business requirement. If the feature requires strict rules and absolute compliance, it follows the path to traditional engineering. Financial gateways, ERP systems, and embedded software belong here because they operate in environments where the tolerance for error is zero. If the feature deals with unstructured data, human language, or complex patterns, it moves toward AI-native engineering. Recommendation engines and customer service chatbots thrive on this path because they require constant adaptive learning. In most modern enterprise applications, these two paths eventually merge into a hybrid microservice architecture. An e-commerce platform uses deterministic, traditional code to ensure that every credit card transaction is processed with perfect accuracy. At the same time, that platform uses probabilistic AI models to analyze the user's history and predict what they might want to buy next. Success in this environment requires a shift in focus. A developer's primary task is now orchestration, identifying the specific nature of a problem and routing it to the architecture best suited to solve it. The future of software engineering is the mastery of integrating both worlds to build systems that are as resilient as they are intelligent.